Everybody, and welcome back. So in the POEMA project, our PhD candidates are known as early stage researchers, or ESRs. So this morning we had Andres, who is ESR6, and we just had Louis, who is ESR7. So I know what you're thinking, and the answer is yes. Our next speaker is ESR8, and that's our very own Felix Kirschner. And he is a PhD candidate at Tilburg University under my supervision. And he will talk about the topic that was very prominent yesterday, namely approximation kernels. So please, Felix, without further ado, the floor is yours.
Thanks a lot, Etienne. Maybe let's check. Can you hear me? Can you see me? And can you see my cursor?
I hear you and see you, and also have a cursor.
Okay, perfect. Thank you very much. Yes, so today I will talk about the construction of multivariate polynomial approximation kernels via semi-definite programming. And well, this whole talk is based on joint work with my supervisor Etienne, who just introduced me. And yes, I think it's good to get right into it. Okay, no, this isn't working. Okay, let's maybe do this. Okay, introduction. So this is the most boring slide, but we will have to go this very quick. So just to fix the notation, n sub n, n to the n sub r is just the set of n tuples, such that the coefficients sum to an integer less than r, and the cardinality of that set will be denoted by s and r. If you see an integer in these square brackets, we mean the set of 1 to n of the natural numbers. And for a subset of Rn, which we will always write with that bold letter k here, we denote the set ck, and this will be the set of continuous functions on the subset of Rn. S to the n will be the set of n times n symmetric matrices, and this symbol here will be the set of positive semidefinite matrices. And well, here we also define the Kronecker delta for two tuples, for two n tuples, which is basically 1 if the tuples coincide in every component, and it's 0 otherwise. And last but not least, we define the trace inner product for two matrices of appropriate size, which is denoted by this these brackets here, and it's just the trace of A transpose B. I think all of these definitions or all of this notation is well familiar to everyone listening, but just to be sure, I wanted to have it on the first slide. So what are we trying to do? We yesterday saw already something about the approximation of functions, and this is something I want to continue today. So given a function f in C of k for just some subset, the aim will be to find an approximation fr of f such that some error is minimized, and the error that we are trying to minimize is just the infinity norm over k. Right? That is the supremum of the absolute value of the difference of the approximation and the function that we want to approximate. So the whole point is basically that we want to have a simple function f, and that simply means that we will want to construct a linear combination of functions which lie in a finite dimensional function space, and the dimension will depend on r. So if we kind of restrict ourselves in the dimension that we're allowed to use, we kind of sacrifice accuracy, but what we gain is something that we can, well, that is more simple in a way that it's, for example, easier to compute or easier to use when you're trying to actually compute a lot of stuff with these functions that you're trying to approximate. So this will be our aim. And let's have a look at the setting. So for mu being a positive finite Borel measure, that is supported on a compact semi-algebraic set K, which will be described by these polynomials Gj here. For such a measure and such a set, we will say that two functions are orthogonal whenever the product of the two functions integrated over K with respect to mu is 0, And just to be sure, we factor out here all the functions that are identically 0 on k, because, well, these would be orthogonal to everything, or at least the integral would be 0, and this is something we don't want. So we don't care about those functions. We just take the space, the set C of k modulo that set. Okay, and well, and you see that the measure that we use kind of important when we define the orthogonality here. So having a sense of orthogonality for functions, we can define orthogonal systems, and just like yesterday, we will have a set of polynomials, which we well p alpha here, where alpha will denote the degree of the polynomial. So this absolute value of alpha just means alpha 1 plus alpha 2 up to alpha n. And now if we suppose that these elements are pairwise orthogonal, which just means that if we take the inner product here, we have some constant times the Konica delta that we defined before, that we can define orthogonal systems if we assume that the set that we have span the space of the whole space of polynomials. Right, and if we have such a spanning set, what we can do is we can expand any function f within that system, and we can do that in the following way. We can write f of x as the sum of a alpha times p alpha, where a alpha is simply p alpha in the inner product with f with respect to mu, and we divide that by c alpha, where c alpha here is the constant that we get here. So these are not orthonormal, but orthogonal, right? So this factor here doesn't have to be 1, can be any positive number. Okay, now what we're interested in today are degree R approximations. So say we want to approximate a function by a polynomial of degree less than R. Then we just saw that we can write f in this expansion that we just saw. So one idea would be that we could simply truncate that sum, right? So we go up to degree R, and everything that comes after that we just toss away, because that would lead to approximation of degree less than R, which is what we do not want. So is that good, or like I mean, we can ask the question, is that a good idea? And in practice, it is not. And the reason for this is something which is called Gibbs Oscillations, which happen close to the boundary of the domain and near points of discontinuity. And we will see a picture of that now. So what I did here is I approximated the step function, which is 1 for every x between between -1 and 0, and is -1 for every x in 0, 1. And the orthogonal system that I used here were the Chebyshev polynomials. And now, if you truncate the series that we saw on the previous slide at degree 64, you get something like this. So close to the edge, also close to -1 and close to 1, you get these oscillations, and close to the point of discontinuity, which is here at 0, you also get these oscillations. And this is something that we would like to get rid of if possible. Good, so we see that truncation isn't the best idea. So what else can we do? And to maybe kind of reformulating the question, conceptually, we are looking for a mapping that takes as an input the function f and sends it to an approximation of degree R, and these approximations they want will just be linear combinations of the orthogonal functions that we defined before. And we simply restrict the set of the functions that we use to functions of degree less than R, right? And now any mapping that does that gives us an approximation FR. And now we would like to look for those mappings that give us the best R as possible. And we can do that by considering kernels, which depend on R. So for every R, so for every degree that we're interested in, we get a different kernel. That takes as input 2 vectors x and y, and is defined by this sum of products of polynomials. So the P alphas are again just the polynomials from the orthogonal system, and then we multiply them together, one with the x variables, one with the y variables, and then we get a kernel. Now this integral operator that I'm going to define now is something we saw yesterday already, and I think the day before as well. So basically, this integral operator takes as input a function, and so what we get in the end will be a polynomial. So this is why I write the x in brackets here. The input of the operator is f, and the argument of the result is basically x, because if we evaluate this integral on the right-hand side, what we will get is a polynomial of degree at most r. And this is actually a straightforward calculation, because if we use the orthogonality relations that we defined before, we can write the integral as a sum like so, and we can just write it a little bit simpler and write this is the sum of all a in n to the n sub r for b alpha times p alpha of x, where b alpha is simply the inner product of p alpha with f with respect to mu times g alpha. And now this g alpha is basically what the kernel that we defined on the previous slide. So let's go back. This is what the kernel actually brings into the picture. And we see that, well, it kind of scales up or down this coefficient right here, right? So these coefficients of the kernel determine the approximation. So for example, if we simply set g alpha to be 1 divided by c alpha, which is, if you recall the coefficient from the orthogonality relation, then b alpha is a alpha, where a alpha is what I defined before here. And well, this would simply be the truncation of the series, right? So at least the mapping that sends a function to its truncation basically is part of the function that we're considering. We know it's not the best one, but it is contained in the set, more or less. Not more or less, it is contained in that set. So, but now the question is, if we know this does not lead to the best approximation, what does lead to optimal degree R approximations? And for this, we get to the next section of this talk, which is general kernel approximation. And yes, I forgot to say at the beginning, I can't see the chat, so whenever there's a question, please maybe unmute yourself and just tell me, or yes. So if there's a question, just feel free to interrupt me. Good. So basically what we would like to do now is classify kernels that are suitable for approximation, right? And it turns out that the following 4 properties are enough for our purposes. And the first one is that the kernel that we're considering should be a function that is symmetric in the arguments x and y, that the integral where we integrate the kernel with respect to y should be 1 for every x and for every r, which kind of means that if we consider the kernel as a density function for fixed x, the resulting measure should be a probability measure. And further, we need the kernel to be non-negative for every pairs x, y, and k times k, and for every r. And lastly, the limit of this expression here should go to 0 uniformly on k. This is a very dense slide, but do not worry about too much, because so we're going to repeat it every time we need it. But we will further introduce 2 quantities. The first one is the resolution of the kernel, which is denoted by sigma r. And it's the square root of this integral, where we integrate the kernel with respect to x and y, multiplying it with x minus y in the square 2 norm. And we further introduce the quantity sigma r bar, which is the supremum of this quantity right here. And the nice thing is that we will able to bound the rate of convergence of the error of our approximation in terms of this quantity here, but more on that later. So what we first note is that the resolution, so sigma r, is less than sigma r bar, right? And why is that? I mean, if we take the supremum here, and we see the expression is almost the same. The difference is that we here also integrate with respect to x. And what you probably also noted is that the expression that we see here is the one in the property for here, right? So we need the kernel to converge to be such that this expression converges to 0 uniformly on K. So if it does, then of course this the sandwich here is true and goes to 0 for r to infinity, and we also see that of course property 4 implies this, but I mean this should be clear, I think. So now about the convergence, the nice thing is that suppose we're given a kernel that satisfies property 2, 3, and 4. So the property 1 was simply the symmetry in x and y. That is not crucial for the next theorem or proposition. Under these three properties, we know by Korofskin's theorem that the or this object here basically converges to f uniformly on K, and the rate of convergence can be bounded in terms of sigma r bar, and I will prove that to you right now. For this, we need to assume that f is Lipschitz continuous with constant L. And this means that the absolute value of the difference of f of x minus f of y is smaller than L times the norm of x minus y. And so this inequality needs to hold for every x and y and k. And now if we assume properties 2, 3, and 4 on the kernel, then one has that uniform convergence that I just mentioned, and moreover the infinity norm of kr of f minus f can be bounded in terms of L times sigma r bar. And the proof is quite short, actually. So we begin by the absolute value here. So note if we take the supremum of all x and k, these three relations still hold. For the first inequality, that is inequality. For the first equality, we simply use the definition of kr of f. And then we note that we actually can, because of property 2, so the integral over k of f of y times the kernel with respect to mu is 1. So we can multiply this term here by 1, and then pull in the function and reformulate it as such. And now pulling in the absolute values, making things bigger, and then using the definition of the Lipschitz using the fact that the function f is Lipschitz continuous, we get this inequality right here. And we see, okay, when we take the supremum here, what we get on the left-hand side is exactly the infinity norm. And on the right-hand side, we get, well, this term here. So it's a supremum of all x and k, where we integrate over k this expression with respect to mu. And now, if we recall that what we defined before, so property 2 gives us that this thing here is a probability measure. So we can use Jensen's inequality, right? And using Jensen's inequality, this is where the square root comes from in the definition of sigma bar, sorry. We can simply, well, then use the definition and see that this here is actually true. Right, and now the proof is complete. Yeah, so any questions about that? This may be a good place to stop. If not, I will continue, and I will continue by giving a very brief description about the Chebyshev polynomials. Okay, good. So let's go through the Chebyshev polynomials really quick. I mean, we saw them in Etienne's presentation as well. So these form an orthogonal system over the interval -1, 1. And yeah, so for this, we define a measure mu on k, and we define it as 1 over pi times the square root of 1 minus x squared. And now the Chebyshev polynomials of the first kind form an orthogonal system, and the nth Chebyshev polynomial of the first kind is just defined as the cosine of n times the R cosine of x. Well, I mean, at least on this interval here, for x in -1, 1, these are in fact polynomials, right? And I plotted here the first few of them. So the first one, the first one is constant 1. Then the second one is just x, and then you get these. Well, you get these first few. So you get a feeling for how they behave on the interval. Now we can generalize those for k being the box -1, 1 to the n, and for this we simply define the product measure. So we multiply the density functions together, and then for any n tuple alpha and n to the n, we define the multivariate Chebyshev polynomial of the first kind to be the product of the univariate Chebyshev polynomials, where well, the index of the polynomial will just be the index, the ith index of alpha, and then we can simply well extend the orthogonality relations, because well, if we're just multiplying together, everything is kind of it doesn't depend on each other, and so we can simply use the univariate orthogonality relationship and see that this actually, so this term here is actually equal to C alpha of the Kronecker delta of alpha and beta, and C alpha is a half to the power of the Hamming distance of alpha. Not the Hamming distance, the Hamming weight. So the Hamming weight of a vector is simply the number of components which are non-zero. So if alpha is a 0 vector, this is 1, and for all others, it's just a half to the number of non-zero components. Good. So now we arrive at something that we kind of saw already in Lucas's presentation yesterday. So we will kind of use a different setting in a way. So we will tackle this whole thing using trigonometric polynomials, because they're easier to deal with numerically. But first of all, what is a trigonometric polynomial? So a trigonometric polynomial PT of degree R is simply something that we can write this way. So it's P0 plus the sum from K1 to R of Pk of cosine of K times T plus P of minus K times the sine of K times T. Now, why is that interesting to us, or why do we need them? The interesting fact is that every trigonometric polynomial of this form right here, so where all the where we have no sine terms, basically, every trigonometric polynomials of this form can give or will give rise to a kernel of this form, right? And these are kernels that we can use, right? So why is that even the case? So just consider the following substitution. Well, if we substitute this, then we arrive here, and we will see why right now. The first one is simply putting in, well, the substitution. And the second step here is a very basic trigonometric identity that we've all seen in calculus, I think. And the next step is simply the definition of the Chebyshev polynomials, right? And so furthermore, so what we can use is that if the trigonometric polynomial PT is non-negative, then the resulting kernel will be non-negative as well, which was the third property that we need to ensure. So here we have the properties again. So we now have a kernel KRXY of this form, and recall that these are the 4 properties that we want to satisfy. So the first one we get for free, because by construction it's symmetric in x and y. And the second property is easy, because we just need to set G0 to be equal to 1, and we get what we want. So now for the third property, you just saw on the last slide that it's enough to have that this trigonometric polynomial here is non-negative. And then we will see what happens with P4 later. But yes, so now to ensure this non-negativity, we simply going to use a Positivstellensatz. And these are, well, especially in the multivariate case, a little easier to deal with than in the regular polynomial case. And for univariate, non-negative trigonometric polynomials, we find that if it's non-negative, then there exists, and it's of degree R, then there exists a positive semidefinite matrix Q of size R plus 1 times R plus 1, such that P can be written as V transpose QV, where V depends on the parity of R. So if R is even, V will have this form, and if it's odd, it will have this form. Okay, so can we use this? Yes, because this already gives us a way to construct kernels in the univariate case by simply solving a semidefinite program. So before minimizing sigma R bar, we will try to find kernels with minimum resolution, which was sigma R, and sigma R squared is simply this this integral here. And again, using the orthogonality relations, we can calculate this. This integral here simply is g0 minus g1, and we know that we have to set g0 to be equal to 1. And now, to obtain a kernel with minimum resolution, so what we can do is simply minimize the resolution, such that this kernel here, which we know via the substitution that we can use, will give rise to a kernel that we want with the same coefficients. So we minimize the resolution such that this expression here can be written as V transpose QV for a positive semidefinite Q, because then it's non-negative, and the resulting kernel will be non-negative as well. Okay, very nice. So also, what's quite interesting, I think, is that this problem can be solved analytically. So when we solve this problem, we will get to the well-known Jackson kernel, and the coefficients of the Jackson kernel are available in closed form. They look like this, and now having them in closed form, we can actually also find an expression for sigma R squared, which is G0G, it's not a G, it's a J, G0J minus G1J, which is 1 minus the cosine of pi over R plus 2, and this is in O of R over 1 over R squared. So yes, that is what I wanted to say about the Jackson kernel. Now in the next step, because to actually bound the rate of convergence of the approximation that we're getting, we need to minimize sigma bar R, right? So yes, for this we will for now jump to the multivariate case just to calculate calculate an expression for sigma R bar squared. And now, well, I'm not sure about the time, and I'm not sure how important that calculation is, but let me tell you this. So in the first step, simply using the orthogonality relations, the only term that survives is the t of 2ei of x, and well, this vector here is 0 for every component but the ith component. So this is the same as the univariate Chebyshev polynomial of xi, the second univariate Chebyshev polynomial of xi. And basically, we can write this sigma bar squared as the sum of these coefficients of the kernel in the end. And so just in the last step, we use the fact that the supremum of C times the Chebyshev polynomial, the second Chebyshev polynomial, is the absolute value of C. Good. So the corresponding semidefinite program, when we minimize sigma R bar, is the following. So we introduce a new variable t which we force to be greater than the absolute value of this 1 minus 2 G1 plus G2, which we just saw in the previous slide, is this term here. If we consider the univariate case, we simply lose this sum, but this expression remains basically the same. So we minimize this expression, which is sigma r bar, and we still want that the trigonometric polynomial that gives rise to the kernel can be written as a well, with a positive semidefinite matrix Q, right? And so these are STPs that we can solve relatively easily. So it doesn't take a lot of computation or computational power for this. And just to get an expression how these two quantities behave next to each other, I gave you a few of the values. So for sigma r and sigma bar r, for one they are the same, and then increasing r, then it seems like well, r is somewhat half as big, but it's not exactly, but so on that order, at least for the ones that I'm showing you here. How do the approximations look like if we use the kernel that we get from sigma r and sigma r bar? And this is what we see here. So the first thing that we notice is compared to the truncation of the series, we get we got rid of the oscillations that we got before, and the approximation that we get looks almost the same, right? It doesn't look like there's a lot of difference between using the kernel of sigma r and sigma r bar, and then increasing the degree, we simply see that we get a better approximation, which is expected, I think. So we can also approximate something like the delta kernel by just taking the convolution of the just said delta kernel. That's not right. We can also take the convolution of the Dirac delta at 0 with the kernels, and then just compare what happens when we take the kernel corresponding to minimal sigma bar r and sigma r, and this is what we see here. So here we do have a difference between the approximations. This is for r equals 32, and then increasing r, we would expect it to get higher and narrower. And this is what happens. So here we have something 8.5 or so, and it's a little narrower. And this is for degree 64, so we doubled the degree here. And now the difference, of course, becomes less, I would say. Okay, so this is the univariate case. This is all basically easy because all the coefficients are easy to calculate. In the multivariate case, things become difficult because, I mean, also for n equals 2 and too high r or too large r, the semi-definite programs that we get are very difficult to solve. But before solving the STPs, we need to write it down in a way that we can actually put into the computer. And that's basically what I'm going to talk about next. How do we even get to the point where we get an STP that a computer can solve? So the multivariate case. Yes. So this is kind of a recall slide. If we define a trigonometric polynomial pk of phi as cosine of k times phi, then substituting phi with r cosine of x, we get the kth Chebyshev polynomial, and this substitution here results in the product of the kth Chebyshev polynomial of x times the kth Chebyshev polynomial of y. And now if we start with a non-negative multivariate trigonometric polynomial of this form here, then we can use the substitution we had before to obtain a kernel of this form here. And now this 1 would correspond to the G0 case, where this product here is equal to 1, this 2 to the 0 is 1, and G0 is 1, which is property 2. Okay, so again, this is difficult to deal with. using Positivstellensätze for you know, ordinary polynomials for the standard monomial basis. So the hope is that, is there something easier when working with trigonometric polynomials? And the answer is yes. So there's a Positivstellensatz saying that if P is a positive trigonometric polynomial, then there exists some integer r and a Hermitian PSD matrix M of order n plus r choose r, such that P can be written as vector transpose matrix vector. Yes, right? So then this is a sum of squares in some sense. Now, one problem is that, of course, the degrees may be arbitrarily large. So we only know that there exists an R in N, but well, it's nice that every positive trigonometric polynomial can be written as a sum of squares. Okay, so writing down the program that we're trying to use, we can simply fix R and then solve the program for that fixed R and look at the kernel that we get. And we can get a kernel where we, again, well, sigma r squared, sigma r bar squared can be written like this. This is something we've seen before on a slide. We just have to ensure that the TIs are larger than the absolute value of that, which we can actually model using two inequality constraints. And now, well, this trigonometric polynomial here on the left-hand side should be able to be written in this form. And now, because I didn't have enough space, I took the, well, just add one equality constraint and write that G gamma is 1 for a gamma is 0 vector. And of course, M has to be Hermitian PSD. Okay, then the first thing that we noted when we did some numerical experiments was that the matrix M is actually, without loss of well, is real symmetric, is what we noted, and then we tried to prove it, and we were able to prove it. So indeed, we can assume M to be real symmetric, which makes things a lot easier on the right-hand side here, because instead of well, looking at that expression, just knowing that M is real symmetric enables us to write this expression like this. So it's just the sum over all alpha beta in n to the n sub r of the cosine of alpha minus beta transpose times phi, then times m alpha beta. And but this is still something which we can't really put into a computer, right? So this is basically what the next slide is about. So the representations in this equality constraint here, they're actually really different from each other, right? So how do we know which of these m alpha betas end up in G gamma? Because here we have a product of univariate trigonometric cosine functions, and here we have a cosine of the sum of these functions, of these phi i's. And well, not to worry, because we've kind of found a trigonometric identity which saves us here. Let I be a subset of this set here. So the n square brackets was just a set of all the integers 1 up to n. And define the function omega I to be the function that flips the index of the input vector if I is in I, basically. And well, then what you can prove is that the 2 to the Hamming weight of x times the product of the cosines of xi is equal to the sum, when we sum over all subsets of this set here. And what we sum are the cosines of the sums of the omega i's of xi. Okay, this is easily provable by induction, but for now you will just have to believe me, because I don't have enough time, I think. So, right. So on the right-hand side of 5, which is this equation right here, we will find all gamma in z to the n, such that we have alpha and beta in n to the n sub r, such that alpha minus beta is gamma, right? And here we can be sure that the gamma is positive, right? So here we will have, or we will get vectors with negative components. But recalling the trigonometric identity I showed you, we can, or we know that we have to make sure that for every gamma in n to the n sub r, the following holds. So the sum of all indices or all components of M for which indexed by alpha and beta, for which alpha minus beta is equal to gamma, we need to make sure that this sum is equal to the sum of all entries of M, alpha, and beta, such that alpha minus beta is gamma I of gamma, no, omega I of gamma, and this should be true for every subset of N, right? Because if this is the case, we can basically factor out the same sum for each of those things here, and then apply identity 6, right? So if we look here, if for every I in N, this sum is equal, then we can simply factor it out, and what we're left with is just applying that inequality, and we get the left-hand side, basically. And then we need to make sure that the matrices that we get are symmetric, but that is easy because alpha minus beta is the same as minus bracket beta minus alpha bracket. So for a given gamma in n to the n sub r, we define the matrix C gamma I. So actually we define that for we define a new set in a minute. But so for every gamma in n to the n sub r, we define the matrix as 1 at alpha beta if alpha minus beta is omega I gamma or omega I complement gamma, and 0 otherwise. And we do this because the resulting matrices, the resulting matrices will be symmetric, because if alpha minus beta is omega I gamma, right, then alpha minus beta, then beta minus alpha is equal to omega I complement gamma, right? Because going to the definition of gamma, well, if I is in the complement, well, then we win this otherwise case, and then exactly the other components get flipped, and we get exactly, well, the other case, right? So to just prevent us from having multiple times the same matrix, we will define script I here as a set of subsets of N. I'll call this set N here. I hope this is not confusing. So as a set of subsets of this N here, such that no complement IC of a set that lies in I, and that the union of all sets in I is the set of all subsets of N. I mean, if I didn't explain it properly, it's not that important. We simply define it so we don't have to get don't have like multiple times the same matrix in the end, because otherwise we would have doubles, right? But anyways, now we can formulate the first set of constraints, which is simply the inner product of M with C gamma of the empty set is equal to the inner product of M of C gamma for every I in I. And of course, we want that to be true for every gamma in n to the n sub r. And then the coefficient of the resulting kernel that we get will simply be a half times this inner product here for any I in script I. So we can just, here we simply choosing the empty set as a representative, right? So we need one fixed point to which we can compare the other ones, right? And when I first implemented this, I thought I was finished, and I didn't get quite the correct result, because I actually forgot something, namely that we need to make sure that some additional terms are 0, because we don't want them, or we cannot, cancel them with other terms. This is why I need to define this set gamma in R. And this is a set of all gammas in Z to the N, for which we have alpha and beta in N to the N sub R, such that alpha minus beta is equal to gamma, and that the absolute values of the components of gamma sum to something that is greater than R. Because, well, we won't ever be able to cancel those out, right? And so what we then do to make sure these don't appear in the sum in the end is adding this set of constraints here. MC gamma I is equal to 0 for every I in script I, and for every gamma in big gamma in R. Okay, so well, the resulting SCP now looks like this. We replaced all the G's with their well, inner product or trace inner product formulation of M and the constraint matrices. And well, okay, this equality constraint here just ensures that G alpha is equal to 1 for alpha being the 0 vector. And this is now the very same SCP that we had before, but simply now we can put it into a computer. Okay, so how do the resulting or how do the results behave? That's what we're going to look at next. So these we already saw, or at least some of them. So for n equals 1, minimizing sigma r squared, we get this line here. And then for n equals 2, we were able to compute the first 25 levels of the hierarchy. For n equals 3, I think we got stuck at this 12. I'm not sure, maybe, so I think it should be possible to maybe go to like 13 or 14, but so this seems to be like the limit. And then for 4, it of course was even more difficult because well, these SCPs get really, really big for increasing values of R. And now, well, maybe as a well, more entertaining part of the talk, we're going to look at some approximations with these kernels. So, oh no, this is the wrong direction. So here you see the approximation of the kernels for the two varied peaks function from MATLAB. This is the function that we're approximating, and so I'm showing you the approximation for each level from 1 to 25, and this was what it looks like. So looking at the actual approximation of level 25 compared to the plot of the function, this is what we get. So at first, when I first saw that, I thought, okay, this looks really, really good, right? I mean, at least the shape works. But if you plot the error and the absolute value of the error, it is not that good for that level. So yeah, it seems like to get like a really good approximation, you need to go a lot higher in the level. But this is what the error looks like. So for some values, you get an error of 0.6 here, an absolute error of 0.6, and well, I mean, it's not like that we have huge huge function values. So I mean, still, so this is also not as nice to look at as this. So I have another approximation for you. So here we're going to approximate the sine of 2 times pi times x times y. And the approximation looks like this. And this is not the peaks function. This is, so this is what the process looks like. And here again, we can just look at the plot of the function itself versus the approximation for level r is equal to 25. And well, here you can see a bit better, like where we're quite far off. Here, for example, and so this is a straight line in the right graph, and it's quite has quite a slope here. So plotting the error, we get something like this. And well, now I'm just going to show you something that you might, or that might be reminiscent of something in Monique's lecture. This is the convolution of the kernels with the Dirac delta at 0, 0. And it looks basically like this. And if you recall Monique's lecture where she had the plots of the optimal SOS density for the minimizers of the Motzkin polynomial, we also saw these things looking like being very close to 0, away from the minimizers, and then going up very steeply. Yes. So, well, let me conclude. And after that, we have time to maybe answer some questions. The problem basically was that the procedure becomes computationally very expensive for large values of n and r. But on the other hand, the coefficients G alpha have to be computed only once, of course, because they're independent of the function f. Now, some of you may have noticed that the problem that we're considering is invariant under the action of Sn applied to the variables, right? So we can permute variables without changing anything. So to improve numerical tractability, what we did is we applied the symmetry reduction to the problem and then solved the symmetry adapted problem, because otherwise we wouldn't have been able to go to level 25 in the bivariate case, I think. So then the next thing is, I mean, it's very good news that the problem is symmetric, because it can be symmetry reduced. But now the other thing is that the symmetry reduction works very well for large n, of course, because the group is a symmetric group on n. But for large R, so fixing n, even with the symmetry reduction, increasing R still makes the problem intractable at some point. Okay, so there is no archive yet, but will probably be coming in the next few weeks. When it's on archive, it will probably appear somewhere on the POEMA website where all the publications are listed. So if you're interested, just have a look there in a few weeks. And now I'd like to thank you all for your attention very much. And I'm ready to answer some questions.
Thank you very much, Felix, for the interesting presentation. So, any questions?
Yes.
I say Bernard.
Okay. Go ahead, Bernard.
I don't hear you. Sorry, Bernard, I don't hear you. Oh, still nothing. So maybe I just ask Didier, while Bernard fixes his sound, maybe you can ask?
Yeah. Can you hear me?
Yes.
Yes.
Okay. Many thanks, Felix, for the nice talk. I was wondering, so you said that these trigonometric polynomials, multivariate trigonometric polynomials, which are positive, are sum of squares, but you mean strictly positive?
Yes.
Okay.
Yes.
Yeah, for sure. No. Okay, thanks. And something I was wondering, so you insist on the kernel to be non-negative. Huh? This is why you use these trigonometric polynomials. But why does it cure the Gibbs phenomenon? I think the motivation, if I understood correctly, the motivation for using kernels and positive kernels in this context is to avoid the Gibbs phenomenon, these oscillations. But why should it be the case?
That's an interesting question. I'm not sure.
You observe that in practice.
Yes. Yes.
Do you understand why?
To be honest, I haven't really thought about it. It's I'm not sure.
And related, maybe, and I will stop with that. A related technique would be what we did with Jean Bernard and Carlos Lasserre and Carlos Arbonian a long time ago. To approximate the volume of a semi-algebraic set, we approximate from above the indicator function of the set. And the indicator function is discontinuous by construction. And so what we do is that we use positive shell and z set to have a polynomial above the indicator function. And so we observe that if we do that and we minimize the L1 norm of the polynomial, we have the Gibbs phenomenon. And so I was wondering whether using kernels you would avoid these as well for this problem.
Sorry.
I was wondering whether if you, instead of using just pointwise that the polynomial approximation lies above the indicator function, for that we use positive challenge z set, but if you use kernels instead for that purpose, whether you would suppress the Gibbs phenomena. Do you have a...
I'm not sure, but it would be interesting to check, right? So,
yeah.
So maybe I can just say, Victor Magron just put a link in the archive. This is a paper that our work was based on. It's called the kernel polynomial method, and there they discuss a bit how the Gibbs phenomenon behaves with respect to the positive or non-positive kernels.
Okay.
So, I mean, this is very classical in approximation theory, but I also don't really know what one can prove about suppressing the Gibbs phenomenon.
Nice, nice. Yeah.
But indeed, this link by Victor is really a very nice explanatory text.
Okay. Many thanks, Victor, and okay, something to understand better as far as I am concerned. Thanks. Thanks again for the nice talk.
yeah, thank you for your questions.
Bernard, do you have sound?
Do you hear me?
Yes, we hear you.
Okay. So yes, thanks for the nice presentation. I have a question about the kernels that you find in the univariate case. Mm-hmm. So are they close to the Jackson kernel? Are they related?
Give me a second, I can go to that slide. So I here at some point compared the values that we get. So here these are the values of the Jackson kernel, right? So this is exactly what you get with the Jackson kernel. So this is basically 1 minus G1, and this is what we get with the other kernel. So you see that. So at least for that, it seems like the Jackson kernel gives here for the G1 something that is a bit bigger, I think, because you have 1 minus. Yeah, so we weren't able to find a closed formula expression for the sigma r bar squared thing. So if you compare the kernel that you get when you use the kernel, like when you minimize sigma and sigma bar r, you see they look quite, or the resulting approximation looks quite similar, and well here as well. So the blue line is where we minimize sigma, and the red line is where we approximate minimize sigma r bar.
And it seems, since you compute this optimal kernel, it seems that the rate is quadratic also in of this other. So the decrease here seems to be quadratic. No?
Yes, but this is for the squared. So sigma r bar squared, right? The actual thing with which we bound the rate of convergence is the square root of that value. So it would be in 1 over R for the univariate case, but for the bivariate case, I think if you analyze the values that you get an estimator of something that is a bit larger than 1 over R. So the exponent is a bit bigger than 1. It's like, I think 1.2 or so, but I'm not exactly sure.
Ah, okay.
I just add that, because we are using a positive linear approximation operator, there's a natural limit to the kind of rate of convergence one can get. So this rate from a Jackson operator is really optimal, basically.
You say it's optimal.
Yes.
So one cannot go below
No.
1 over R square.
No, not for at least there are classes of functions for which you cannot do better than that. Yes.
Hello.
Yeah.
Jean-Bernard.
Yes, I have a remark about the approximation of the Dirac delta function. So it seems to be painful in degree to approximate this as a function. I mean, you want to be a peak at x and positive or almost close to 0 otherwise. And this is very hard with a positive kernel. Now, if you approximate the delta Dirac function if you look at the Christoffel-Darboux kernel k of x, y as a polynomial in y, so it is not positive. It has a peak at x, but the important thing is that if you look at the moments of the Dirac measure at x up to degree r, the degree r, this degree r polynomial has exactly, so it is a sign measure, and it has exactly the same r moments as the Dirac delta. So for approximation, it is not good to take the CD kernel, but for the optimization in the SOS lower bounds, it is exactly this property that we have. The CD kernel, the Christoffel-Darboux, approximate this view as a polynomial in y. So k of xy, you fix x and you look at as a polynomial in y. It has a peak at x. It mimics the Dirac delta function. And of course, it is not positive function. It is not positive on the axis as a y polynomial, but as a density, as a sign density on 0, 1 or minus 1, 1, it approximates all the moments up to degree r are exactly the moments of the Dirac measure. And this is exactly what this is exactly these properties why the SOS lower bounds is good and has exact finite convergence. So in other words, the CD kernel is not very good for uniform approximation, but to approximate the Dirac delta function as a sign, as a measure, you approximate it by the sign measure, who has the sign density, but the sign density has exactly the same R moments as a Dirac delta measure. So it's another, it was just a comment.
Yeah, no, it's an interesting remark. Thank you.
Yes, so in the reference that Victor just sent, it's actually shown that if you use the Jackson kernel, the approximation to the Dirac delta is actually very close to the Gaussian. This is actually very close to a Gaussian with the right variance. So that where the variance is basically order 1 over r or 1 over square root r. Yeah. So any other questions? I don't see any hands. Oh, okay, Jean's hand is still up, but I think he asked already. Okay, so if there are no other questions, I would just quickly like to thank some people who were involved in this workshop, because we've come to the end of this part of the workshop. But of course, I'm too fast. We should first thank Felix again for a very nice talk, Felix. So thank you again, Felix. So I would just like to thank a few people who were involved in organizing this part of the workshop. Tomorrow we will still have the ESR day for the PhD candidates, and I think some of us who are not PhD candidates will also be there. But let me just thank people who were involved in this part. First of all, Cordia and Riner, who was my co-organizer of the scientific program. And then, of course, the invaluable Lynn and Nguyen. She helped with the website, with all kinds of administration. She's also putting all our slides and all the recordings on the website. So thank you very much, Lynn. And in Tilburg University, our secretary, Ingrid Meder, helped to organize everything, because until the last moment, we thought we would have an in-person component to the workshop. So we had everything organized, and alas, in the end, it was all for nothing. But still, she put in a lot of work, so I would like to thank her. And of course, to all the speakers and also all the participants. Without you, we would not have a workshop at all. So thank you very much. And let's have a round of applause for everybody. Thank you very much.